Welcome to this video on digital electronics. In this video, which is the third in the series of combination logic circuits, we will be discussing about multiplexers and demultiplexers. We will be looking into the operation of multiplexer and demultiplexer and implementation of Boolean expressions using mux and demux. First, a multiplexer. A multiplexer is basically a data selector. It selects one of the outputs from many inputs using select lines. So, a multiplexer selects a single data line from several data input lines and the output from the data line is available at the output. It is basically a digital switch with many inputs to one output. So, for 2 per n inputs, we have n select lines and there is one output. Let us look into a 2:1 multiplexer. A 2:1 multiplexer, there are 2 inputs and 1 output line. So, since we have 2 inputs, we require 2 per 1, that is 1 select line. So, this is the block diagram, a 2:1 mux. There are 2 input lines, 1 select line and 1 output line. So, this select line, for a given value of select line, one of the inputs is selected. Let us look at the truth table also. So, when the select line is 0, the output is D0. So, that is when select line is 0, this line D0 selected and D0 is available at the output. When select line is 1, D1 is the output. So, when select line is 1, D1 is available at the output, and the logic expression for the same is y is equal to D0 into S dash plus D1 into S. The logic diagram for the multiplexer. So, we have the select lines, the line and the complemented form available, and we have 2 AND gates which are used to select from one of the inputs and then an OR gate to select the output. So, when select line is 0 to this AND gate, the input D0 and this complemented form. So, we have one there. So, D0 is available at the input of the OR gate and D1 and this is 0. So, 0 is available here. So, it is D0 or 0 and we have D0 at the output. So, that is given by this expression. When select line is 1, here this becomes 0. So, D0 into 0, it is a 0 here, D1 into 1. So, we have D1, D1 is available at the output. So, this is the logic diagram of a 2:1 multiplexer. Next, a 4:1 multiplexer. A 4:1 multiplexer means 4 input lines and 1 output line. The number of select lines that we would require is 2 square, that is 2. So, 2 select lines are required. Using 2 select lines, we can select from one of the 4 input combinations. So, the truth table for the same is here. The select lines S0 and S1, the combinations from 0, 0 to 1, 1 are available. So, when the select lines are 0, 0, D0 is selected as the output. So, for 0, 0 select line, we have D0 as the output. For 0, 1 combination, the output is D1, and for 1, 0 it is D2, and for 1, 1 it is D3 as indicated in the table also. And this is the logical expression for the same. So, the logic diagram for a 4:1 mux, 2 select lines are available, both the lines in the complemented and uncomplemented form, and then we have 4 AND gates where the 4 inputs are given and then the combination of select lines. For D0 it is S0 dash S1 dash, for D1 S0 and S1 dash, for D2 it is S0 dash and S1, for D3 it is S0 S1. So, for the specific combination of the select lines S0 and S1, the output from one of the AND gates is input D0, D1, D2 or D3, and the rest are all zeros, and that is odd and we get that as the output. Now, pause the video, design an 8:1 multiplexer. So, an 8:1 multiplexer, we have 8 inputs and 1 output. 2 per 3 is 8. So, 3 select lines are required, and this is the logic diagram for a 8:1 mux. Next, let us see how to implement a higher order multiplexer using lower order multiplexers. So, first designing a 16:1 mux using 8:1 mux. A 16:1 mux, that is 16 inputs, therefore, we would require 4 select lines. 2 power 4 is 16, 4 select lines for a 16 mux, and for an 8:1 mux 3 select lines are required. So, we shall use 2 8:1 mux to have 16 inputs. So, multiplexers, 2 multiplexers are chosen and the inputs are given I0 to I7 and I8 to I15 to the 2 multiplexers, and the select lines are all connected. S0, S1 and S2 are connected to the 3 inputs of the 8:1 mux, and the 4th select line is given to another 2:1 multiplexer, which will choose between the two 8:1 multiplexers. So, now when S3 is 0, the lower multiplexer is chosen, and when S3 is 1, the upper multiplexer is chosen. And for the combination of S0, S1, S2 from 0, 0, 0 to 1, 1, 1, one of the inputs from the lower and the upper multiplexers will be chosen. For example, when S0, S1, S2 are 0, I0 over here and I8 in the other will be selected and given as input to the 2:1 multiplexer. So, if S3 is 0, I0 is selected, and if S3 is 1, I8 is selected, and that appears at the output. So, this way we can go in for all the 16 combinations of output, and this functions as a 16:1 multiplexer. Next, designing a 16:1 multiplexer using 4:1 mux. So, 16:1 mux requires 4 select lines, 4:1 mux requires 2 select lines, and to have 16 inputs using 4:1 mux, we would be requiring 4 such multiplexers, and so these are selected, and to each of the multiplexers 4 inputs are given. 4 such multiplexers, we have the 16 inputs that are given. Using 2 select lines, one of the inputs of the 4 inputs of a multiplexer is chosen, and you will have another multiplexer, 4:1 multiplexer with 2 select lines given there, which will select from one of the 4 inputs of the multiplexers. The output of these 4 multiplexers are input to the 5th multiplexer, and one of these inputs will be chosen as an output. So, here when we have select lines S0 and S1, it is 0, 0, we have I0, I4 also being selected, similarly in the other multiplexers. Now, when S2 and S3 are 0, 0, I0 is selected. If it is 0, 1, I4 is selected, so on. So, this way we can implement a 16:1 mux using a 4:1 mux, that is 4 4:1 mux plus additional 4:1 mux. So, totaling 5 4:1 mux to implement a 16:1 mux. Next, let us see how to implement logic expressions or Boolean expressions using multiplexers. So, here for the given logic expression, the number of input variables are determined, and from that the corresponding multiplexer is chosen first, and then corresponding to the minterms in the given logic expression, the inputs that correspond to the minterms are connected to logic 1, and then the remaining inputs are connected to logic 0, and the input variables are all connected to the select lines of a multiplexer. Let us see with an example. So, this function f of x, y, z is sum of 0, 2, 6, 7, the minterms. So, we have 3 variables x, y, z. So, we need to use a 8:1 mux. A 8:1 multiplexer is chosen, and the variables are given as select lines to the multiplexer, and the minterms are 0, 2, 6, 7. So, D0, D2, D6, D7 are all connected to logic 1, and the rest are all connected to logic 0. Let us see how this functions. For select line 0, 0, 0, D0 will be selected, and that will be the output that appears, which is connected to logic 1. So, the output is 1. For 0, 0, 1, D1 is selected, and that is connected to logic 0. So, the output is 0. So, this is how the logic expression can be implemented using a multiplexer. So, pause the video, solve the problems that are given. So, the first problem, decide on the type of multiplexer required, and then the second question, implement a full adder using 8:1 mux. Draw the truth table for a full adder, the sum and carry. There are two output variables, so use two multiplexers to implement the two Boolean expressions. In the previous slide, we had seen how to implement a logic expression using a multiplexer where the number of select lines was equal to the number of variables. But now if we have a multiplexer with the number of select lines lesser than the number of variables of the given expression, let us see how to implement it. So, for this example of function of ABC, a 3 variable input, if we have a 8:1 mux, we can draw the truth table and the outputs where the min term is equal to 1 can be connected to logic 1 and the rest to 0, and we can implement it. But in the problem, we are required to implement the function with 3 variables using a 4:1 mux. Let us see how to proceed with that. First, let us draw an implementation table. In the first row, write down all the inputs of the multiplexers D0, D1, D2, D3. So, we have 4 input multiplexer, indicate the 4 inputs. And the 3 variables available, let us give 2 of the variables to one select line and another variable as an input. So, D0 corresponds to BC00, D1 corresponds to BC01 and D2 10 and D3 is 11. So, that is what is indicated here. This corresponds to BC00, 01, 10 and 11. The other variable A is given as the input. So, A dash, that is A is 0 and A is 1. Now, write down the min terms. So, 0 0 0, a 0 here, min term 1, 2, 3, 4, 5, 6, 7. Now, from the expression, look at the min terms for which values are 1. Write them down on the table and circle all the 1s. Now, look vertically down column wise. So, the first column we have 2 zeros, both are not circled, so write down a 0. In the next column, 2 ones which are both circled, so write a 1 here. The third column we have a 0 and a 1. Look at the variable, input variable for which it is circled, that is the value is 1, that corresponds to A. So, write down a A. The next column, one of the outputs is 1 which is circled, the other is 0. So, write down A dash over here. So, let me repeat it. So, look at each of these columns vertically. If both the columns have 0 and they are not circled, write down the 0 as an input. If both are circled, then write down 1. If one is circled and the other is not, then write down the variable corresponding to the circled row. Okay, it could be a A dash or a A. Now, draw the multiplexer, give the inputs and the select lines, mark the variables, and the inputs D0 corresponds to 0, D0 has a value of 0, give a 0, D1 is 1, D2 is A and D3 is A dash. So, give this as an input to the multiplexer and draw the output. Here in this problem that we have considered, we have given A as input and BC as the select lines, but any one of the variables could be given as input and the others selected as the select lines. In that case, the numbering of the min terms over here will vary. For example, if we had C as the input and A and B as the select lines, then here this will correspond to AB and C dash and C over here. In that case, the min terms will be 0, 1, 2, 3, 4, 5, 6, 7. So, any of the variables can be given as a select lines and any for the input, but correspondingly the min term should be marked correctly. So, pause your video, implement this given function using 8:1 multiplexer, check your answers and proceed. Next is a demultiplexer, which is nothing but a data distributor. Here we have one input and many outputs. So, from one input many outputs are got and the select line determines to which of the output the given input is available. So, for 2 power n outputs we have n select lines. So, basically a demultiplexer has one input to 2 power n outputs with n select lines. So, let us see how to implement a 1:4 demultiplexer. So, as the name indicates, one input, 4 outputs. So 4 outputs we require 2 select lines, and this is the truth table. We have 2 select lines, so the values could range from 0 0 to 1 1. When the select lines are 0 0, the input D in is available at output Y 0. So for 0 0, data is available at Y 0. For 0 1, the data is available at Y 1. So for 0 1, input data is available at Y 1, and for 1 0 in Y 2 and 1 1 at Y 3. Let us see the logic diagram of 1:4 demultiplexer. We have the 2 select lines and the complements of which are also available. Since this is a 1:4 demultiplexer, we have 4 AND gates, and the data input is given to each of the AND gate, and for the corresponding output each select line combination is used. The first output, it is S0 dash and S1 dash, second it is S0 and S1 dash, then S0 dash S1, S0 and S1. So for the specific combination of the select line, one of the outputs is high, the rest are all 0. So at one of the outputs of the AND gates, D input is available, the rest of the outputs are 0. Pause the video, implement a 1:8 demultiplexer. Next is how to design a demultiplexer using lower order demultiplexers. So design a 1:8 demux using 1:4 demux. So 1:4 we have 2 select lines, and then the enable line is used, to which the third variable is given. So the enable line is given as such to one of the demux, and inverted and complemented input is given to the other. So for ABC, when A is 0, the first demux is selected, A is 1, the second demux is selected, and BC combination for 0 0 to 1 1, each of the outputs is available. So we have 8 outputs from the 2 1:4 demultiplexers. So let us implement a full subtractor using 1:8 demultiplexer. First draw the truth table, the 3 inputs A, B and the borrow input, and we have the output of difference and borrow output. Draw the truth table. Now since we have 3 inputs, 8 possible combinations are possible. So use a 1:8 demux and decide on the minterms from the truth table. So we have the expression difference is minterm 1247 and borrow is 1237. Now in the demultiplexer, select the corresponding outputs for which the minterms are, the values are 1, and OR it, and we get the output. So we get the difference and the borrow. So in this video, we had seen implementation of a multiplexer and demultiplexer, and we had also seen how to implement Boolean expressions using both a mux and a demux. So these are the references used. Thank you.